four main types of discontinuity. So number one would be the removable discontinuity. Usually it's the function that has a hole in it, and it's called removable because while doing some basic algebra, you can actually get rid of that. Let me show you an example. We have a function of x squared minus 1 over x minus 1. We see the hole in the graph. It means that function is not continuous. This is where it breaks, exactly at that point. So in order to find where that point is located, we have to set up our denominator to 0. We have x minus 1 equals 0. We just bring 1 to the other side. It gives us x equals 1. So this is where we have the discontinuity, when x is approaching 1. So in order to solve this equation and try to remove that discontinuity, we have to rewrite it this way. Let me just change the color. As limit of x approaching 1, x squared minus 1 over x minus 1, we can actually identify the difference of squares in numerator and rewrite it as limit x approaching 1, x minus 1 over multiplied by x plus 1 over x minus 1, and we just easily canceling out x minus 1. Next, we have to write the limit all the time, x plus 1. At this point, we can just plug in the value, and it's going to give us 2. So our limit is located at x approaching 1 at 2. So it's located right over here. But if we're going to go one step back, we see that when we canceled out our x minus 1 in numerator and denominator, we got a function of x plus 1. So if you would try to plot it on a graph, it will give you the exactly same linear function as displayed over here, but it's not going to have that hole and it's going to be continuous. Okay, next, we have infinity discontinuity. Let's consider the function f of x equals 1 over x. As we can see, from the left side, it's going down. It's going to negative infinity because it's never really approaching 0. So it goes down. And from the right side, it goes up. It goes to positive infinity. So in this case, since our left side and right side, they don't agree with each other on the same value, it means that the limit does not exist. But there is a vertical asymptote at x equals 0. What is the vertical asymptote? It's pretty much the point that will never be intersected. It might be approached at infinity, but since it never equals infinity, it's just approaching, we have the vertical asymptote at x equals 0. Next one, it's jump discontinuity. So it's not really the function that will be defined only by one equation. Because there might be two equations. Like over here, you can see that on the left side, the green one, it's defined by f of x equals x plus 2 when x is either less or equals 1. This is why you have a filled hole over here, and here you got just like empty hole inside without a fill. Because f of x equals 2x only when x is greater than 1. So if we try to plug 1 in that function, it should return us 3, but not 2, because it belongs to the green equation. And in this case, we also do not have a limit because this function is discontinuous at x equals 1. And the last one is oscillating discontinuity. As we can see, we have a function of sine 1 over x. If you would zoom it out and check it on Desmos or somewhere else, it looks just fine, but the more you try to zoom it in, the messier it gets when this function approaching 0 from the left and right side. And since it's oscillating discontinuity, it means that there is no limit because it's alternating between 1 and negative 1. When it's approaching 0, you cannot really identify at which value they meet when they approach 0. So it means the limit does not exist in this case.